So in the last set of videos, we took a look at Newton's first and second laws of motion and had a bit of a discussion about mass. Now here we're going to pick up the thread and take a look at Newton's third law. And again, I will quote Sir Isaac in translation directly. He says, "To every action there is always opposed an equal reaction, semicolon, or the mutual actions of two bodies upon each other are always equal and directed to contrary parts." Now the reason I highlighted the semicolon is actually in the first several editions of the Principia, the book that Newton wrote summarizing mechanics. The sentence ended at the semicolon. But he found that even among his contemporaries, he needed to clarify it a little further. And so in later editions, he added the bit after the semicolon. So let's go through and say, what does this mean? First off, the big deal that he added to it, all physical interactions are mutual. Oops. Now, what we mean by that is the two players that are interacting interact with each other at the same time. And also, more to the point, it's not just say you can't have a one-sided interaction. It's always two objects interacting with each other. So object A can't exert a force on object B unless object B is also exerting a force on object A. The equal and directed to contrary parts. Nowadays we would say oppositely directed. So the way to think about this is that both players in the interaction will feel the same force. The same force in opposite directions. So, for instance, if you go and push on, let's just say, a box or something like that, and you push on the box to the right, the box will also be pushing on your hand to the left. And if you push on the box with 10 newtons of force, the box will push on your hand with 10 newtons of force. Further emphasizing the mutuality, we also get that all interactions are simultaneous. So you pushing on the box to the right and the box pushing on you to the left happen at exactly the same time. Nobody comes in earlier than the other. They're both at exactly the same time. And also, further highlighting the mutuality, all interactions are of the same type. So for instance, if one object is interacting with another via the gravitational force, if A attracts B gravitationally, then B will attract A gravitationally via the third law, not some other way. Now there may be other interactions happening between A and B, but if A is interacting gravitationally with B, will interact gravitationally with A. Or with your hand on the box, you exerted a normal force on the box, and the box pushing back is exerting a normal force on you. So this leads to the idea of an action-reaction pair. Or they're also known as third law pairs. I'll probably use both terms roughly equally. So these are the pairs of, so when we're going through and looking at a system, these are the pairs of forces where we can identify that the forces are the same type on different players, same magnitude force, oppositely directed. And we'll find as we go along, sometimes this will help us to figure out the direction of not so obvious forces. So let's just start by thinking about a book sitting on a table. All right, so there's your book sitting on the table. Now let's go ahead and draw a free body diagram for the book. So if you want, you can start by doing a force identification diagram. If we draw a circle around the book, we see that the circle cuts through the table. So there must be a normal force from the table on the book, and I'll be extra pedantic when I'm writing these for reasons that'll become apparent in a moment. And then we ask, are there any, and that's it for contact forces. It's not moving sideways. So then are there any long-range forces? Yes, there's gravity. And since the book is just sitting, I'll say force of gravity on the book. And since the book is just plain sitting on the table, we know the acceleration is 0. So since the acceleration is 0, it must be the case that the two forces add up to 0. So these forces are equal and opposite. So now you should ask yourself, are these a third law pair? So go ahead, pause the video, think about it for a second, and I'll get back with you. So the answer is these are not a third law pair. They're in fact what I'd like to call a second law pair. That's where you get a pair of forces that, because of the requirements of Newton's second law of motion, in this case, since the acceleration is 0, the forces had to add up to 0. We only had 2. And what happens is that they're equal and opposite. That's two forces that happen to be equal and opposite, but notice these two forces are on the same object. To be a third law pair, they would have to be on different objects. Also, the two forces involved are different kinds of forces. This is gravity here, and this is a normal force here. Those are not the same kind of force. So it flunks the different object test, and it flunks the same kind of force test. So this is a pair of forces that happen to be equal and opposite because of the requirements of Newton's second law of motion on the object. So like I say, I like to call that a second law pair. So let's go and identify the third law pairs to these. Well, we can go and take a look at, the table. Let's draw the table in blue. So here's the table, and it's sitting on the earth, and there's still that physics book sitting on it. So now if we draw a force identification diagram for the table, there's no way we can draw a circle around it without it cutting through both the physics book and the Earth. So if we draw a free body diagram for the table, what we'll have is we will have a normal force from the Earth on the table. And as this cuts through from the book, there's also a normal force from the book on the table. These two are a third law pair. And notice how they're on different objects. So third law pairs will always appear on different free body diagrams. When you find a third law pair, what I'd like to do is for the first pair I find, I draw a single slash through each of them. For the second third law pair I find, I would do 2 slashes, then 3. After a while it gets cluttered and I usually switch to X's or something like that, but give each third law pair its own little unique mark. Other people prefer drawing dotted lines and so forth. Now I'm not done yet. There's still a long-range force acting on this. There's still also the force of gravity acting on the table. And if I were doing a better job of drawing this, I would be making this vector substantially longer. So there we go. Now, what about this force of gravity acting on the book? Who would we have to draw a free body diagram for to find that one? Think about that one for a second, and then I'll get back with you. Okay, so to find the third law pair for the book, the answer there is it's the Earth. So here's the Earth. Yeah, I'm just going to draw a circle for the Earth. And sitting on the Earth is a book, is a table with a book on it. Okay, so we can do the same thing. We can do a force identification diagram for the Earth. Now, of course, there are plenty of objects interacting with the Earth, so I'm not about to be drawing every single force acting on them, on the Earth, just the ones relevant to the table in the book. I can lump all the other objects together into the Earth itself so that I can ignore them. That turns out to be something we can rigorously do, and we'll show that later. So let's go draw our free body diagram for the Earth. So ask yourself, are there any contact forces? The answer is yes. There's a normal force of the table acting on the Earth. And it's trying to push the Earth down. There is our second third law pair. So the Earth is pushing up on the table exactly as hard as the table is pushing down on the Earth. Now, there will also be long-range forces acting on the Earth. Specifically, the table will be attempting to gravitationally attract the Earth up. That's a third law pair. And also the book. So I'll use an X for that one there. So now we have found all of the third law pairs for the book, and as an added bonus, we figured them out for the table while we were at it. So this may be leading to a question that is, well, if everything is pulling on everything equally hard, how can anything ever move? So to that end, let's think about a tug of war. Whoops. So we'll have this guy here. They're happy because they're going to be winning the tug of war. Got a river flowing between them here. This person here is, whoops, not terribly happy, mostly because they realize they're about to get really wet. But by Newton's third law, actually there's a couple of third law pairs you have to, there's a couple of pairs you have to think about. One is that the player on the left is going to be pulling on the rope, and the rope will pull on the player on the left equally hard, and same for the player on the right, but the force is due to the tension in the rope, so those should be the same as long as we neglect any acceleration, and otherwise it's not a big deal. So we'll just neglect, we'll say that the rope wasn't accelerating at this exact moment. And so then you can argue that the two players are pulling on the rope equally hard. So how are we ever going to have a winner? Well, it turns out, sorry about that there. Turns out that the way you're going to have a winner is that the Earth is going to push harder on the winner. So I'll say this is the force of still static friction of the Earth on the winner. And here we'll have the force of static friction of the Earth on the loser. And then here, since this is just about where we're going to win, this is force due to tension, that's force due to tension. The tension in the rope is the same. They're a third law pair. So if you take a look at here, I should probably draw in some normal forces and gravity while we're at it. So there's normal force from the Earth on the winner. Same length there. Should be a force of gravity on the winner. Here's a normal force on the loser. There's a force of gravity on the loser. And again, those normal forces and gravities are each equal and opposite, but they're second law pairs, not third law pairs. And this is because the two players are not accelerating vertically. So what we get here is that the winner is going to feel a net force to the left, as is the loser. Now, how is it that the Earth, quote unquote, knows to push the winner harder than the loser? And the answer is it doesn't, of course. What's happening is the winner is pushing into the Earth with their feet. And so if I were to draw a free body diagram for the Earth here, again, I'm going to neglect a whole bunch of other forces on the Earth, so just bear with me here. The winner was pushing into the Earth with their feet, and that is a force of static friction. So the winner pushed on the Earth, and the Earth pushed back on the winner just as hard. Whoops, 2 slashes there. And then with the loser, the the loser was also pushing with their feet into the earth. So this is the force of static friction of the loser on the earth. And the earth pushes on the loser just as hard. So the moral of the story is that the winner of a tug of war is the one who pushes harder with their feet. Okay. So in the next video, I will spend a little bit of time talking about the force of gravity. So catch you in the next one.